Welcome today. So we're really happy to host Professor Charbon today. He's a professor at EPFL, leading the Aqua laboratory. He's also one of our 3 members of the eSpace steering committee. So we're also very happy to hear about more in details about his current research. And the name of his topic today is SWIR NIR SPAD image sensor for LiDAR and quantum imaging applications. A few housekeeping rules. So we recommend people to turn off the video during the discussion. You can write your questions if you want throughout the talk in the chat. We will do the Q&A session at the end. So the talk should be, Eduardo, like 30-40 minutes. So we have time also for questions and answers. And at the end of the talk, people want to ask the question orally, they can raise their hand and we'll unmute. But if you feel more comfortable in writing your question in the chat, I will also read the questions. So that was it. Welcome, Eduardo, and I will let you with your presentation.
Thank you very much, Emmanuel. It's a pleasure being here. Thank you very much again for inviting me. I hope the sound is good. So I'd like to start thanking the people that make this possible. And these are my PhD students, postdocs, and of course, the Swiss National Science Foundation, European Commission, as well as other private contributors. So I'd like to start with solid-state photon counting, and I'd like to tell you something that most of you probably know already, which is the fact that single-photon detectors have been around for some time, at least from the 1930s, where photon counting was done using tubes, essentially tubes in what are known as photomultiplying tubes, or PMTs. Essentially, an incident photon was by photoelectric effect converted into electrons, and then these electrons eventually would be amplified by multiplication until they reach the anode, and then they would be amplified electrically and therefore reveal or detect a single photon. This has been brought to extremes by, you can see here the variety of PMTs, from the large ones to the small ones that you can see here. This is a photograph from Amatsu, but many other producers exist that have created over time this type of detectors. What we're going to talk about today is a relatively new detector known as single-photon avalanche diode, or SPAD, also known as Geiger mode avalanche photodiode, or GM-APD. Unlike PMTs, this detector is basically a reverse bias diode. Conventionally, reverse bias diodes are biased at relatively small voltages, but if the voltage, the bias voltage is increased, one can achieve avalanche breakdown. So that means that in principle, you can multiply detection of photons into multiple electrons. Now, the problem is that if you operate in this regime, you're going to have an optical gain that is difficult to control. So you can do it maybe for a couple of devices, but if you have millions of devices, you're not going to be able to control it very well. So an alternative to that is to operate in Geiger mode. So here you operate above breakdown, and if you operate above breakdown, the gain, optical gain, is in principle infinite. So in order to do that, you have to operate above the breakdown voltage VP by an excess voltage known as excess bias voltage VE. And if you operate here, of course, to avoid the destruction of the device, you will have to have a quenching mechanism that I'll talk about later. So this is how the detector is built, and is comprising an anode, and junction, and a cathode. And it can be made in planar implementations. In planar implementation, of course, you require guard rings to avoid edge breakdown. So this structure is much smaller. The voltages involved are much smaller, not kilovolts, but rather tens of volts. And most importantly, it can be implemented in CMOS. CMOS, for those of you that are not familiar, stands for complementary metal oxide semiconductor. And it really created the revolution because for the first time, one could build the planar SPADs that would be essentially CMOS compatible or CMOS. So basically they can be implemented in a standard process. The advantage of the standard process is that first you manage to reproduce it. And essentially once you find the right combination of layers, you can have always working SPADs. It's reliable. And most importantly, it's miniaturizable. So that means that you can build a very large number of them. And using the economy of scale in CMOS, you can build millions in a relatively small space. This is what the Aqualab has generated over time, starting from the very first 4x8 detector to very recently the first megapixel SPAD. But along the ways, there have been many different SPADs, SPAD arrays or SPAD imagers for many, many different applications. And we're going to touch upon a few of these applications. Of course, the economy of scales, Moore's law, is enabled over time to go from the original 0.8 micrometer technology to 0.35, and then very recently leading to 4565 or even 4562 nanometer technology and so on. So here are some of the examples of the detectors built in the various technologies. As of 2012, 3D ICs have been introduced. So in that case, you can build the SPADs in one layer, and in the other layer, you can perform operations using standard CMOS. So I'll talk about this in a moment. Of course, the performance has dramatically improved over time from the beginning, the early 2000s to today. So today we have actually established a few records. One of them is the timing resolution that we can achieve at 7.5 picoseconds, sensitivity that reaches 78 to 90% even, and fill factors in the order of 80% with the help of microlenses. That time has also improved, and that means that you can detect more photons in a short amount of time, while dark counts, that basically is a measure of noise, have gone from kilo counts per second of CPS to single digit CPS and now milli-CPS with cooling. After pulsing has also reduced dramatically, thereby reducing correlated noise. The power of integration enables not only the reduction of the size, but also the integration of electronics together with the detector. So this is an example of a monolithic detector that has quenching transistors. Those are the transistors that prevent the destruction of the device when you have an avalanche, implemented together with a feedback loop, for example, for a fast recharge that enables a very quick 1.5 nanosecond dead time. And of course, most importantly, the wave that you see can be converted into a digital signal. Once you have a digital signal here, you can implement a digital following circuit that essentially does that can perform any functionality that you like. So as mentioned, PDP has grown dramatically. So these are examples of 54% at 480 nanometers. At 420, for example, you can still have 38% or higher. And the DCR, as mentioned, the dark count rate has gone dramatically down with temperature, but it can still be reasonably low even at room temperature. But the real name of the game here, the real advantage is the timing resolution. So this is an example of this detector that even though it's a diameter of 25 micrometers, it can reach, as of recently, an SPTR or single photon timing resolution down to 7.5 picoseconds. So this is an example of what you can do with these detectors. This is a time light in flight that was achieved. So essentially blocking and freezing the light as it propagates in space, thanks to the capability of multiple images taken with the MegaX, which is the megapixel chip. So here you can see the whole propagation of a total of about a meter in a very short amount of time, 6 nanoseconds or so. This is another very interesting example of light propagating in a fiber, and then you can see the dispersion as it propagates. This is a very interesting phenomenon that can actually be used as a spectrometer. But of course, all of you will probably appreciate LiDAR or light detection and ranging that is enabled by fast single-photon avalanche diodes, in arrays, and in this case, Velodyne is actually using APDs. But the principle is to build and to reconstruct a 3D image using the time-of-flight detection. Okay, so how do we build a camera out of a single SPAD? Well, we've seen that we need a quenching circuit, we need a gating circuit, but then what we do with the pulses that come out of it? Well, we can perform counting, and we can perform time of arrivals. So this is an example of a TDC or time to digital converter that allows you to do that seamlessly. So if you have space, you can in principle build the TDCs on electronics or other types of devices, essentially outside the detector. So that allows you to get a fill factor that is relatively high. But this is a little bit of cheating because actually you push electronics wherever you don't need to be sensitive. And then when we will have 2D detector arrays, then you will have a problem. So this is a detector that was built for JPL NASA. And with this detector, we were able to build an array of 1,024 SPADs by 8. And we were able to use a gating very, very precisely to achieve gating the order of 700 picoseconds. And so these are the SPADs that in this case, they're not round, but they're square, thereby improving the fill factor. And then this is a detail of the SPAD. The photon detection efficiency was 9%, typical. And this is the PRNU, the photon response non-uniformity of 1.2%, with a 700 picosecond time gate. So you can see here the uniformity achieved with a very large detector and a very short gate. With this, we could build a Raman spectroscopy. So you can see here the Raman emission, for example, using sanbornite, barium, or you can use LIBS, which stands for laser-induced breakdown spectroscopy. And the intention was to build a detector capable not only of building spectra for minerals at a certain distance, but also to move around as on top of a rover. So that was the idea, to be able to essentially point at various rocks and analyze them and figure out the composition without touching them at a certain distance. So this was intended for Mars, but now we're thinking that it could actually be used on the moon or perhaps on asteroids. Okay, so I anticipated the problem, and that is it's all good to go one dimension, but what if you want to go two-dimensional? So for two-dimensional arrays, you need to either place the electronics on pixel, which reduces further the fill factor, or you can put it on a column, or you can put it behind if you have access to 3D stacking. So if you are building a 2D detector, of course, you're going to have some limitations, and you're going to have to read out the content using some techniques, some mechanisms. One of them is known as frame-based, where basically everything is exposed for a certain amount of time and read out all at once. But one could think of having an event-based or event-driven approach, where basically as long as there are no photons, there's nothing being read out, but then photons will drive the readout themselves. Or you could think of a reconfigurable device. And I'm going to give you an example of a reconfigurable device. This is called LinoSPAD, which is a reconfigurable one-dimensional array of 512 by 1 SPADs. And you can see here the wires that connect every SPAD to the exterior. So here in the PCB, we connected all those onto an FPGA. But this is a photomicrograph of this of a small fraction of the SPAD. You can see the SPADs with micro lenses on top. And here you can see the resulting pulse analysis of the spectrum operating on a TDC that was actually implemented on the FPGA itself. But alternatively, one could imagine reconfiguring the FPGA to build a bunch of counters, for example, or counters with gating, or perhaps a single TDC or multiple TDCs, and exactly based on the given implementation or application that one wants to use. Of course, micro lenses can be added, both in front side illumination and in back side illumination. And this is an example of optical micro lenses that were built on our device. And here you can see a detail. And here you can see the gain of fill factor that is achieved by micro lenses, depending, of course, on the F number of the lens that you can put in front of it. Of course, the larger the F number, the better the concentration factor. You can also implement micro lenses electrically by basically creating an horizontal electric field that will lead the detected electrons into the multiplication region. That has a double advantage. The first one is that it can reduce the multiplication region, thereby reducing the DCR. And the other is the fact that in principle, you can reutilize all the space that was not sensitive to light. How do we scale up such a device? Well, first of all, you need to reduce the pixel pitch. Now the current record is established by us is 2.2 micrometers, but one could think of reducing that further, and we have preliminary results at 1.8 micrometers. But that, of course, requires a 3D integration. What is 3D integration? 3D integration or 3D stacking can occur in two ways. One way is to build a SPAD onto a detector, then reverse the detector and hybrid bond it into a bottom chip that implements the a functionality of, for example, counting on TDCs, then performing thinning, and then implementing and illuminating from the back. Another way is to use the front side illumination, or not reversing the detector, but placing the detector on top of the bottom chip, and then by view of through silicon vias, connect the two chips. So these are two examples of, on the left-hand side, the backside illumination chip implemented in TSMC technology, 45 nanometers on top, 65 on the bottom, and then recently 22 nanometers at the bottom, or 180 on both sides. And here you can see the step given by the thickness of the top chip, and you can see indeed the capability of connecting through pads at the bottom. If you're using BSI or FSI, you can put on top of it micro lenses. These are examples of micro lenses on top of the TSMC chip to increase fill factor. Let me give you a couple of examples here on how one can use the SPAD. So we talked about LiDAR. So how do we actually build a LiDAR? A LiDAR principle is very simple. You have a source of light that you direct towards an object. The light is reflected, and all you have to do is basically measure the time that it takes, or time of flight. Then you can reconstruct the distance based on the notion of the time of the speed of light and the time of flight. Let me make a small digression related to coincidence detection. So when you have a SPAD that is exposed to light, it is exposed to the laser light, but it's also exposed to background illumination. So we know that when the SPAD is emitting, when a laser is emitting light, it emits many photons. And if one can somehow count these photons at very short amount of time, then one can build a so-called coincidence window that will be able to enable me to distinguish the photons emitted by the laser from the photon from the background. So the photon from the background here is represented in gray, and the ones from the light are represented in red. So by performing coincidence, in this case, by detecting, for example, a threshold of 4 photons, one can separate very easily the background illumination from the illumination coming from the laser. So in this case, the coincidence failed because he could only find 1 photon, which happens to be background, and therefore not being able to recognize any event. So if you do this, you can essentially recognize, of course, strong signals with respect to background noise, but you can also recognize the same signals or smaller signals even when they're immersed in background noise. So this was done externally, so with very little use of filters, an exposure of 4 kilolux in the outdoors at very large distances. So this was done on the roof of one of the EPFL campus buildings. You probably recognize it just in front of the PM building. And this is the measurement that was done up to 100 meters with a reflective target of 50% down to 10%. And then you can see here the error in the order of 10 centimeters or so. You can also perform flash time-of-flight imaging, where you measure simultaneously onto a very large number of points on a surface. So this, you can see the classical checkerboard, which results to be exactly flat, which is what you would expect. And this demonstrates the independence from time-of-flight measurement on the reflectivity. And here, reflectivity can vary from 10 to 50%. Of course, if we want to build this type of detectors, you need large format cameras. So this is an example of MegaX, which corresponds to the very first, the world first megapixel SPAD camera with a pitch of 9.4 micrometers. We could achieve 24,000 frames per second with this camera, and only a voltage of the order of 24 micrometers or so. So in this case, the image that I showed of the light in flight was achieved with a gate that moves in time and allows you to reconstruct the response. For example, this can be used in multiple reflections, and also it's very easy to reproduce on a pixel by pixel basis. So this is a 2D image that was reconstructed with a detector, and a 3D image, a LiDAR image that was achieved by the same detector. But one of the things that maybe some of you are wondering about is that, can you also do quantum imaging? The answer is yes. There are many quantum imaging modalities that one can do, from a quantum LiDAR to ghost imaging and so on. So I'd like to give you a couple of examples here, starting from the quantum LiDAR. So the idea here is to generate quantum entanglement first. So basically a pair of entangled photons. So this is a Wikipedia definition of entangled photons, which I let you read. The idea is to send a pair of entangled photons onto a target, and then to recognize the idler and the signal. And then here we can essentially use two properties of the entangled photons. One is to be synchronous, and the other is to be center symmetric with respect to a lens. So if you do that, one can, for example, hide information. So create a so-called classical information and superimpose it with a quantum information. And then by use of multiple images with a fast detector like ours, one can distinguish the classical image from a quantum image. This is very useful, for example, for information hiding, but it's also interesting, for example, in another application, quantum distillation, that has two images that one can recognize from each other, and quantum LiDAR, where in this case, the classical image is the background, and the quantum image is the object of interest obtained with by reflecting entangled photons. So this is a quantum LiDAR setup that was set up to distinguish the quantum reflected image in 3D from the classical image. So here you can see, and you can see the movie corresponding to this recognition in our website. Okay, so I'd like to conclude my presentation with giving you an outlook for SPAD cameras. And I'll give you 5 points. The first one is related to 3D imaging. So one can combine different technologies, for example, gallium arsenide on top for sensitivity in near infrared. This is an image from Argo that has built a 32 by 32 array and even a larger array. And we are actually building larger and larger arrays. So this is one that we built in collaboration with NRC in Canada as a PDP of 50% up to 1.6 micrometer wavelength. And this is the bottom tier that can support up to 96 by 96 detectors. Here you can see a comparison between state-of-the-art InGaAs and indium phosphide detectors. You can see the PDP in a vertical axis and horizontal axis at ECR. This is at room temperature, and this is a cryogenic temperatures. By cryogenic temperatures, I mean 225 Kelvin. So you can see here that the PDP is quite large, can be quite large, and the DCR is very reasonable still. And here the pitch, the jitter that we can achieve down to 116 picoseconds, which is actually quite reasonable for LiDAR applications. One can also combine hyperspectral single-photon imaging to integrated filters. So this is an example obtained by my student Shufan Zhu, that she actually was able to implement an array of 4x4 differently spaced filters that you can see here. This is a simulation, and this is the measurement that she achieved using a DBR, a cavity, and another DBR. So this can be implemented in our CMI facility and placed on top of the detector, so thereby enabling hyperspectral images together with single-photon images. One can perform coincidence also and real-time G2 computation. This is basically a type of interference analysis, can be used, for example, for HPT, Humphrey-Bryan twist type of detectors. And so in this particular case, it was used for the analysis of the hemoglobin content in the human brain. And this is done in SWIR 3 by use of 2 different gates. So instead of using a single gate, a blue gate, we also use a red gate that allows me to achieve a temporal aperture of 100%. So this is an example of this detection achieved with a relatively small number of pixels. This is published work published by our friends in a collaboration with our friends in Edinburgh, Professor Robert Henderson, and these are the same results obtained with 1 pixel and with multiple pixels, 1024, as well as with the improvement that can be achieved here with using 250,000 pixels, like in the case of SWIR 3. Embedded computation is also a very interesting approach that can be done on ASIC, on an FPGA, and on a processor. So a couple of examples here. This is a detector called Piccolo in combination with an artificial neural network for the interpretation of fluorescence lifetime imaging microscopy images. So this has eliminated the histogram and replaced it with a neural network. The advantage is, of course, to be much more compact and quite accurate. This is a setup that we built. Without going too much into the details, let me jump to the results. And here's a movie of this setup that was achieved that allowed us to achieve film images in real time. You can think of building neural networks on chip. So this is an example of a chip called MindHive, where we build a neural network on the bottom of an array of SPADs with their own electronics. And with this, you could actually imagine having very extensive images. I'd like to close with SPAD imaging in space. This is images that were that was given to me by David. And here you can see some of the issues that you have in space. One is the fact that you have a very large dynamic range, given by the fact that you have specular reflections. You have very fast images, potentially, and also, maybe two-color type of surfaces, like on the moon, for example. So you want to get very large speeds and at the same time very large dynamic range. These two properties are usually difficult to achieve simultaneously, but with our detectors you can, by virtue of the fact that you have very, very fast SPADs, and essentially you can detect single photons. So if you're more interested, we have a lot of activities starting with David, and please contact him if you would like to have more information. His vision is, of course, to build extreme robotics, and in combination with the detectors and fast independent control in space. So I'd like to leave you with conclusions. So I'd like to show you this Moore's law for SPADs one more time, to really impress on you the fact that the importance of this economy of scales achieved with Moore's law. And who knows, maybe embedded AI could be the way of the future, using more and more advanced technologies. So if I have to leave you with three messages, is the first one is that SPADs really has emerged as a technology of choice for many applications, especially in quantum imaging. And I show you just a few examples, but there's more coming. 3D stacking could be very important in the future, but multiplying the impact of these detectors, introducing not only parallelism, but also machine learning and other advanced techniques. And finally, that photon counting together with embedded ANNs could be ideally suited not only for quantum imaging applications, but also for space-based applications. And with this, I'd like to thank you, all of you. And this is an image of our user group meeting. These are all the people using our detectors at the moment. Mm-hmm. And hopefully this group is going to include some of you in the future. Thanks.
Thank you very much, Eduardo, for this presentation. We have a few questions in the chat. So the first is more practical. Will the slides be available for?
Yes, of course.
Okay, of course. Then we have a question. I think it was on slide 24 when he asked 23 or 24. Was this light propagation display an animation? It was when he asked the question. I think it was when you had the picture with the car, you know, the beginning when we were talking about LiDAR.
24 is
23 maybe, so maybe. When was the?
This one.
Yes. There, yeah. Is this an animation?
No, this is actually a measurement.
A measurement. Yeah. Okay.
This was done by Velodyne. It's not done by us.
Okay. Slide B. Okay, that was this one, and from the same person is in free space as the distance increases, there is possibility of loss of photons, attenuation. How is this detected?
Maybe I can refer back to the image that I showed earlier on the high distance. And actually, it's true. The farther you go, and the more photons you lose. And then in addition, you have this issue of the background illumination. So in this particular case, there are a few photons coming back. But the problem is not detecting the few photons coming back. The problem is not being overwhelmed by the photons that come back from other sources. And so there's many solutions here. The coincidence detection is one. There's another solution proposed by people in Canada, in the University of Toronto, proposed using other types of mixing signals and something similar to lock-in amplifier. But the bottom line is, I think what the question was is that what if you don't get any photons? If you don't get any photons, then you have a problem because there's no way to go by. So with one photon, obviously you're going to get a measurement with a large variation, but you need more photons to reduce the variation. So you will need to take, I think, the best possible resolution, the timing resolution, and at the same time, the largest number of photons as possible. And then if this means cutting down on the background illumination, well, then there are techniques. I mentioned one, but there are many more based on gating, for example, or sliding gating or progressive gating, etc.
Okay. Then do we have any quantum light sources and detectors in existing space missions?
I don't know the answer to this question.
Do you know?
Maybe you should relay the question back to you or to David.
No, I think that for, as far as I know, at least in imaging, we don't.
Okay.
I don't know if maybe in time of flights, like one single pixel in the time of flight maybe has been used, but I'm not aware of that.
Yeah.
Either.
Okay. So we might.
But one thing that I would like to mention is the fact that even if you don't have sources of entangled photons, you can use large sources like the sun. The sun has large number of entangled photons that are emitted at any point in time. So if you can detect these pairs, then you should be able to somehow utilize these sources indirectly.
Which is good. And someone mentioned in the chat that we should fly this technology. Which we tested. So then there is a question from Hans-Peter Kehl. What is the combination between robotics and SPAD? You would be more interested to get to know more about it. He would be interested to get more, more about it.
Okay, I'm not expert in robotics, so I think I know something about SPADs, but not on robotics. So I probably defer the question to David.
Can you repeat the question again?
So the question is, what is the combination between robotics and SPAD? Would be interesting to get to know more about it.
I see. Well, this can be a very long conversation. To make it short, like a potential application of SPADs in robotics, particularly for space, is the increase in reliability, right? So if we look at some of the maybe not newer, but hot topic sensors that are being used, like event-based cameras or like just normal stereoscopic, conventional cameras, or even LiDAR, they will require of an additional optical sensor, right? You will never go with just simply a neuromorphic camera to space. So what's interesting about SPADs is that it allows us to overcome that need by being able to do both, right? So in that case, for instance, in the comparison with neuromorphic cameras, we could extract the event point clouds, if you wish, while at the same time being able to take intensity images of the scene, which is a great advantage. Again, some of the applications that Eduardo mentioned about having, faster speeds, so being able to have actual, faster rovers on Mars or on the Moon, being able to have high resolution images from LEO satellites as well. That's a big advantage. So we're launching more smaller satellites that fly at lower altitudes, but imaging with those satellites is becoming increasingly more challenging with conventional technologies. So SPADs could help there as well. But the answer is probably longer than that. That's just an example. Hope it helps.
Yeah. Yeah, he got it.
Okay, cool. Otherwise, send me an email.
Yes. There was the email mentioned in the presentation that is already yes at EPFL. Let's see.
Yeah.
I will write again in the chat. Christophe Pache from CSCM is asking on slide 55 or 56. There is a picture of a checkboard. Was it acquired with a 2D SPAD array having 1 TDC per pixel or shared TDC?
There are no TDCs here.
Okay.
This is obtained with the same detector. So we superimposed the 2D image and the 3D image. This is a detector I did not describe in detail because it would take maybe 20 minutes just for this detector, which implements, but I'll be happy to discuss in more detail. This detector actually has clusters of 16 by 8 pixels, SPADs, that are organized with a TDC, so that the TDC is there, but is not one for pixel, is one for cluster. And so what happens is that essentially, if a photon is detected inside the cluster, a counter is started, and that counter counts within that cluster how many other photons are detected. And if there are more than one detected, it will open a window of 500 picoseconds. If more than one is detected, and it assumes that the light comes from the laser and it takes it. And then the first photon and all the other photons following are going to be converted through the same TDC into codes that represent the time of arrival of the photons. If less than one photon, I mean, just one photon is detected, then it is assumed to belong to background and it's discarded. So the result of the TDC is actually sent out to the exterior of the chip. Now, one thing that I would like to notice is the fact that since we have a single TDC for a cluster of 8 by 16 pixels, we have to use a mechanism known as decision-making detectors, if you like, that are basically fast logic that is used to take the input coming from all the photons, from all the detectors in the cluster, and redirect it to a single TDC, maintaining the information about the origin. So this allows you to share a single TDC over an array of 16 by 8, for example, could be 8 by 8 or more or less, without losing information about the origin of the photon being detected. But at the same time, not losing spatial information, because the decision-making tree is actually maintaining the time of arrival. It doesn't degrade it by more than a few picoseconds. So this is the technique that we use in this particular detector.
Okay. Then in the same question, there was, I don't know if you maybe answered, but could you also please comment on PVT resiliency and how this may affect the distance measured on the checkboard from pixel to pixel?
Okay. No, I would not. I did not mention PVT. I mentioned the sensitivity of TCR to temperature. And the rule of thumb is every 10 degrees, you double the TCR, dark count rate. So you definitely have to be aware of the temperature. And that is very important in space because there may be some large variations of temperature which need to be taken into account. Nevertheless, this can be done automatically. And since the characterization can be done a priori, it should be possible to compensate for that. That's T. P is very, very limited. P refers to process variation because it's a digital process. And so the variations between components across very large chips even, it's in the order of a few picoseconds. So it doesn't really matter as long as you have ways of compensating or calibrating the TDCs. So this is variations across the chip, and variation from chip to chip are even less concerning if calibration is in place. But calibration has to be in place in some way. As for the V, voltage variations, yes, these are concerned. So again, for the digital section, there's very little variation because the signal being digital, it's very resilient to variations in VDD, as you know. But variations in excess bias voltage, which is the voltage in excess to the breakdown voltage that is used for SPAD, will change the sensitivity by a bit, a few percentage. So one wants to use an excess bias voltage that is as high as possible, because the higher the excess bias voltage, the lower the sensitivity to breakdown voltage. So in other words, a very small variation of breakdown voltage will result in less and less variation at the pixel level of PDP. So there's always an interest in increasing the VE, the excess bias voltage, as much as possible.
Okay. Then we have a question on how the performance of SPADs is affected by radiation damage in space applications.
Yes, I should have added the slides, indeed. We've done extensive characterization of SPADs for ESA. So that included gamma radiation up to 3 megarad, proton variation that up in 2 different energies, 11 MeV and 60 MeV, positrons, electrons, and even X-rays. And the results are summarized in a thesis by one of my students, Matt Fishburne, that you can find online. And it can also be found in a few papers that we published, highlighting the fact that the sensitivity is very minimal. PDP stays practically unchanged, where DCR, the dark count rate, can increase, but it can go back to reasonable values after annealing. And that can be done with active annealing or passive annealing. There's one effect that we have observed, which is interesting, known as RTS, random telegraph signal. So what happens is that the DCR changes between 2 values, or in some cases 3 or 4 values. And this is due to traps that are introduced by irradiation. So the RTS pixels is usually a very small number of pixels. So we have a paper by Karami back in 2009 that talks about that. But of course, after proton irradiation, we've observed that the number of RTS events increases. So that is an indication of an increase of traps that can be, as I mentioned, in part be reduced by annealing, and in part also reduced by electrical means, which I did not describe here.
Okay, I think it's a very detailed answer. Next one was, is there any concept of distributed detection? I'm not sure if these terms make sense in optics. However, in networks, this makes sense to increase the resilience and security of receiver in the IoT world. Distributed detection could mean that multiple detectors are used to construct one image.
Yes. Well, I wasn't thinking about IoT, but I can mention a project known as a Quasar or Quasar by Roland. His last name escapes me. Walter. Roland Walter is an astrophysicist based in Geneva, who has had this idea of using HBT for a number of applications in astronomy. And HBT could be used, I mentioned briefly G2 when I was talking about G2, and could be used, for example, in large telescopes. But we are also discussing about combining these images from telescopes placed at very large distances from each other. So, and of course, since we perform HBT, we need to synchronize them to the picosecond. So the detector that we are building for Roland and Quasar is going to have a resolution in the order of 20 to 30 picosecond, full width and half max. And it will be over large surfaces to perform also spectroscopy in principle. And it will have techniques to synchronize with other similar detectors at kilometers or meters, hundreds of meters distance. And the reason why we want to do that is precisely what the viewers mentioned, is to improve robustness. One could think, of course, of applying this technique maybe at a different scale in IoT. And in that case, the main concern is, again, synchronization. How do you synchronize different IoTs? So there are new techniques that just came out, like the White Rabbit, for example, has been around for just a few years, which are protocols that could be applied to achieve synchronization levels of the order of a few picoseconds, even in low-cost, low-power type devices at variable distances using fibers, or perhaps even using radio frequency to achieve this. I'm more a believer of optical methods, so one could imagine having the IoTs connected optically with each other, so building a network which will have cameras for detection and also maybe reutilized for communication, or maybe separate detectors for utilization. If you have an idea of a project and you have finance, I'll be happy to participate with detectors.
Very good. That was so the person says thank you. There's still a little time for a few questions. So in the chat there was no more, but if someone wants to raise their hand and also ask a question or perform a comment, feel free. I see no hand raised. No additional questions.
Can I ask one?
Yeah, do.
Sure. So I actually wanted to learn a bit more about these coincidence detection. Mm-hmm. So when you were to have, if you were to have multiple, let's say in the future this gets into consumer products and we start building these detectors on vehicles, right? And you have millions of these signals been bounced on highways and roads. Can you still discern what's coming from your own detector and what's coming from?
Of course. I attended the thesis by one of Peter Zeid's students maybe 10 years ago or 12 years ago. And he proposed to use a technique known as CDMA. Okay. So code-based multiple access. The idea is to send pulses that will be modulated in position, so using pulse position modulation. Mm-hmm. So this way you can essentially create a code that corresponds to a certain distance. So at the same time, you can build for each and every one of the measurements, you can measure the time of flight. And by doing so, you can simultaneously have information about the depth of the object that you're looking at, and at the same time recognize what is the generator, who has created has generated the pulse. So this way, every pulse could be coded differently and detected differently, independently. So it turns out that the problem with the CDMA is the fact that you need a large number of pulses to recognize, of course, that particular laser. And it turns out at the end of the PhD defense, the conclusion was that a fairly good way of distinguishing different sources is to simply have them out of sync. So if you have essentially cars that will send sequences of pulses that are completely out of sync from each other, you'll have already a very good way of distinguishing your own pulses from those coming from other sources. One way is basically dephasing them, so having lasers out of phase, but another way is having lasers that are slightly out of frequency. So also if you have different frequencies, you can build this way of being independent from each other. Of course, the most obvious way is to perform, to have filters, for example, optical filters, very narrow, plus minus 10 nanometers, for example. And then every car would be assigned a different wavelength. As you know, lasers are slightly different, so not all the lasers are the same. So if you could combine a certain laser with a certain filter, then you'll be able to be uniquely able to detect that particular light. I spoke very recently to a company that makes LiDAR, and they told me that this is actually not acceptable because the variability is so low, and actually that's for consumer application, this is not good. So I have to give you the disclaimer about that. But I can think of other techniques that one could use. One of them is using, of course, variable, or to apply the idea of CDMA, but instead of applying it on the number of pulses and the type of pulses and the length of pulses, the position of pulses, also the position of the gates. So combining gates with a TDC, for example. In this way, you would be able, again, to use the fact that there's a slight different emission from the others, and then to be able to distinguish those. But the question is valid, of course, maybe not in space, but in the future where everybody will have a LiDAR, this is going to be a very valid issue. So coincidence, I think it's probably the way to go, because also distance is going to help you. As the previous attendees mentioned, of course, the larger the distance, the less the fewer the photons. And that's actually going to help you, making you independent from other cars that will be at the larger distances.
Great. So thanks so much.
Thank you very much.
So I think now we're getting at the end. There was one last question, but maybe it's pretty general. If we use the quantum imaging, what changes? Materials, control systems, what are the benefits? Higher precisions.
Okay. Well, that's a very open. Well, let me just give you a quick answer, very quick answer. When one can talk about quantum imaging, the first question that comes to one's mind is quantum advantage. So what is the quantum advantage you get with this technique? That's a real question to ask. Not really increased precision, not really increased robustness, maybe, but the quantum advantage. So what is it that you can do with a quantum imaging technique that you cannot do with a conventional classical technique? I think I would like to leave you with this, but just to frame the question in a way that is actually very useful. And this is a question that is always asked in papers by reviewers and in conferences. What is the quantum advantage? It's not always easy to answer because you have to show that you cannot do it with classical illumination. And the answer is not always straightforward.
Great. So thank you very much for everyone who attended this seminar. I think it was really successful because we had a peak participation of 40 people, and now we have 28 at the end. So for us, it's a great success. We also saw there was a good variety of attendance, so from EPFL, but also outside EPFL. So I see also that we do the communication with space innovation. So that's the Swiss network is also connected, because there was a question also from our colleagues in the Hochschule and CACM. So I'm happy for that. So it might also give some inspiration to create some new projects and get some nice applications.
Absolutely.
So thank you very much. If you have further questions, I'm sure Eduardo says open for questions or by email. I also share the email of David for the robotics applications. I remind that we have more or less one seminar of this kind per month, or plus minus. Candice just shared on the chat also the list for the events. We have the newsletter also you can sign, so you have all the updates, and you can follow us also on LinkedIn, where we also put all the links to this seminar. So thank you very much, everyone. Thank you, Eduardo, also for
thank you very much.
The time. For David also being there, and we keep you for the next seminar, which will take place. Candice, remind me, when is the next date?
I think it's November 13th.
November 13th, but still to be confirmed. And
to be confirmed.
Thank you very much. Goodbye.